Hello, everybody. Thank you for joining us today. My name is Emily Kuda, and I'm Percona's Senior Manager of Marketing Programs, and we're going to get started in just a moment. For those of you that are joining us, you will be on mute. If you have any questions during the discussion, go ahead and enter those in the question section of the control panel. At the end of the webinar, we're going to take time to answer as many questions as we can. Any questions that could not be answered will be addressed in a follow-up blog entry on Percona's database performance blog. So with that said, I'd like to thank you for joining us today. We're going to be talking about how to improve MongoDB performance with proper queries. If you'd like a copy of the slide deck, I've made it available in the handout section. There will also be a copy of this webinar sent in a follow-up email address with the slides and the recording. So, without further ado, this webinar is going to be presented by Percona's software engineer, Tim Vaillancourt. Take it away, Tim.
Hi, everyone. Like Emily said, my name is Tim Vaillancourt, and I've worked on a few technologies, but really the only one that matters in this talk is Mongo, or Percona server for Mongo, MongoDB. That's my introduction quickly. So we'll look at document design, query operators, indexes, evaluating the performance of these queries and operators, good practices to follow, common issues, and then we'll go answer some questions with the time left. We'll start with document design first, because that's usually where you start with Mongo. Usually you need to insert data before you read it. So how you design that data is very important, and probably one of the most important topics to avoiding scalability problems down the road. We won't talk about sharding today, but you have to worry about document design with sharding, with the shard key. That's covered in a lot of other Percona blogs and articles, and is maybe its own webinar. But also with document design, it's good to worry about data types early, because it's hard to change, let's say, a terabyte of data after it's written. It's easier to get it right the first time, if you can. So before we go too far, Mongo is a schemaless database. So unless you're using validation on your collection, which is a feature that actually throws errors if you try and insert the wrong types of data, like MySQL, by default, Mongo won't do this, and that can lead to apps that succeed in functionality but aren't very efficient. So what I mean there is you can store data in a very inefficient way in Mongo if you're not careful, because of its schemaless nature, which is actually a benefit in another way. But you can actually kind of create a bottleneck in your app if you're not designing your documents right. So we've got the really simple case here of two collections. So when you see db dot in Mongo, the next name after that is the collection, similar to a table. So here we're looking at two documents in two different collections, one called people and one called addresses. You'll see this sometimes when relational database apps have moved to MongoDB and haven't really considered the difference in the document model. In relational databases, you usually store things in very separate tables and join together at query time those two things. So actually, in a relational database, having people and addresses in separate tables would actually probably be a good idea. In Mongo, it's actually designed kind of the opposite way, that any joining you would want to do in your application is already done in your document. So here's a bad example, again, that just going through it again, that it's got the object ID of the address document on the bottom. The first document, the people document, has a link to the addresses document. How you would typically do this in Mongo is more like this, where you would embed the address document, because Mongo can actually support nested documents. This is going to be much more performant to query because there's no join, and that's one of the biggest benefits of the document model in Mongo, is that if you're using a relational database where you're doing something like 10 table joins to do reads to the front page of your website or your product data or anything like that, it's very, very fast if you can make that a primary key lookup, which in Mongo is a document. If you can get an index on a single document, it's basically a primary key lookup and a single document read from the storage engine. So this would be, instead of in a relational database in the model that we looked before, that would be 2 reads. This is 1 read. And hopefully by the object ID that has an index. You can create deep levels of nesting in documents, but there is I believe, a limit of 100 in Mongo, a configurable limit. But don't go too far, because it actually just becomes hard for the application developer to write queries. So if you have, let's say, 10 layers or 20, 30 layers of nesting in your document, it just becomes very ugly in your code to actually query that, because you have to write 10 to 30 layers of nesting in your code. So don't go too far, but definitely take advantage of the fact that you can avoid these joins. It's easier to query the top level fields, of course, but yeah, 30 layers down is not fun. And perhaps the most efficient, or the most important thing you could do for efficiency of in the document area of your design for your queries is actually make sure your data types are correct. And I'll explain last why that's important, but I've got 3 examples here where in red we have a date in quotes, which makes it a string in Mongo. If we stored that as an ISO date, which is a real timestamp date object in Mongo, that would store in 48% of the space, because strings are kind of opaque to Mongo. Mongo has an efficient way of storing dates called ISO date, which is just a type in Mongo, 48% smaller if you're using string dates. If you're storing numbers, this is an 8-digit number on the second line. That could store as a real number. So if you ever see a number with quotes around it in Mongo, that means it's a string and it's not storing efficiently. If you don't see quotes around a number, that's a real number. And if you're using an 8-digit number in quotes, for example, it would be 25% smaller as a real integer. Same with Boolean, 53% smaller if you store true as a real Boolean instead of the word true as a string. It seems pretty obvious, but unfortunately, that's one of the biggest problems I ever see in schema design, is strings being used or wrong data types being used. So why this is important is your indexes are actually bigger. So if you put an index on, let's say, the date on the first line, that index is going to be almost twice the size on disk, because we're using an inefficient string format to store a date. If we used an ISO date and put an index on that, you probably see where this is going, 48% smaller index. And that translates to memory because your server automatically caches indexes. You could be using 25 to 53% less RAM in these examples here if those were indexed fields that were queried often. So that's getting a little down in the details, but that's kind of the biggest mistake I see in document design. Next is query operators. So let's assume we've followed those recommendations in the last section, and we've got some good data types. Let's start to look at how we'd actually query this. So Mongo uses a JavaScript-like query language. It kind of looks like JSON. And when you're starting out, it kind of looks confusing because it's not using words like SQL uses words like select, from, where. Sometimes brackets and commas aren't quite as friendly to new developers on Mongo. So I'll just explain that quickly. But once you get the hang of it, you'll actually notice that simpler things look harder in the syntax, but much more complex things look easier. So if you're doing extremely complex things in Mongo, I find if I tried to do that in SQL, it would have been pages and pages of something not so obvious. So the second line here is showing an example of a Mongo query, or actually this is doing a command here, db.collection.command. And breaking this down, db is the database variable in the shell. Collection here is actually the collection name, similar to a table in MySQL. And after the collection comes the command that you want to run on that collection that usually takes in a JSON list of arguments. We'll show some examples of that. So this is probably the most common operation you'll ever do on Mongo, which is a find query, similar to a select in MySQL. So in the example here, we've got db.foo.find, and in the brackets, we've got a JSON document that says name Joseph. So this is going to use the field document field name across the entire collection foo to try and find a match on Joseph. That's going to return the entire document, and if there's many documents with name Joseph, it's going to return all of those documents. So MongoDB documents can be up to 16 megabytes in size. So sometimes you don't really want to return the entire document if it's very large in storage, if you only wanted one piece of that document. So in the second example here, I've added a second option to the find query in a second set of braces. I've made that bold. That just says name one, and that's telling Mongo that I only want the name field to be returned. And by default, Mongo will also return the ID field, which is a default unique ID for the document. So the second query could be a lot more efficient if that document that matches Joseph was 16 megabytes in size, and I just wanted the name. This second query is going to be much more efficient because I'm just returning an ID and a name instead of a large document. That's important. And really, just to compare to MySQL again, the second example, it's really similar to using select star in MySQL is frowned upon because you're just going to select every column. Usually you should know which columns you want, so same principle here. For numeric and date types, it's possible to use greater than, less than operations that you might expect. They use $GT, $GTE. You can probably see the pattern there. And they can be used in find queries in braces, basically, so in its own subdocument. So the first example, we have a greater than equal to 1, less than equal to 10. So the first find query is basically doing a range query between 1 and 10 on the field code. The second query is using in on a specific array list of values. So another thing that you can do in MySQL also. It's possible to check if a field exists in Mongo. So because Mongo is schemaless, usually all your documents should have the same fields, but let's pretend we've rolled out a new release to our app and we've added a new field. Older documents won't have that field, and it might be smart to, when we do our queries on that field, to check if it actually exists, because we might just scan a whole bunch of old documents trying to find the address field in this example, and maybe it's not there. So that's another nice feature in the find query is the $exist operator, which you can set to true or false. And that using an index can be quite quick and tell you if a document has the field at all before it's compared at all. By default, if you add a comma list of conditions to your find document, that just basically makes it an AND operation. So everything you add is basically just an AND. So there's two ways of writing AND queries in Mongo. The first one in the example here is a $AND array. And we have two different JSON documents, one looking at the name field, one looking at the address exists true. but that can actually just be rewritten as the second line, which because by default Mongo uses an AND operator for multiple conditions, both of those are the same in the end. I think the second one is more readable though. The OR command, of course, isn't the default, so you'd have to specify that if you wanted to use OR. OR runs more than one query in the background, so it's kind of unpredictable if you're doing multiple OR conditions, how much of an impact that query could actually have. But if you actually use $in, $in, that's a much more efficient way of doing the same query. So we have two examples here of basically the same query. We want to know code 1 and code 2, but the $in query on the second line is going to be much quicker if there wasn't an index on that. So actually, this is a bad example, but the $or will collection scan, so scan every document in the collection if every condition doesn't have an index. So in this condition, both of the fields is code. So that might not be a good example, but if we had two different fields, so let's say code and author, and only one of those had an index, or can't use an index unless all of them do. A $in can only operate on a single field, but will use an index. So I hope that makes a bit more sense. Hopefully you can use a $in a query instead of a $or for that reason. Regular expressions are also supported, but probably not advised if you can. If you're writing a search engine, then of course you have to use regular expressions, but because regular expressions aren't very efficient compared to equality matching or range matching on numbers, usual database operations, I would try to avoid it. But if you need to do that, basically using forward slashes in your query, so this find query with name Seth in forward slashes is actually going to do a regular expression search. If you're doing a lot of text-based searches, you might want to consider the second approach that I have here, which is using a text index and the $text feature. And I won't go too far into that, but that's a feature in Mongo that uses a different type of indexing, which is efficient for text. And you can put one text index on a collection. So that if you're looking carefully at the query with the $text, there's actually no field specified. That's because a collection can only have one text index, so it already knows what field you're asking for. And this is just an example of using a lot of different operators at once to do a single query. And all of the operators that we've shown can be stringed together in a way to answer your problem. So knowing what to query is good, but maybe that's not going to run efficiently without indexes. So let's talk about that. Like most databases, Mongo uses B-tree indexes. Aside from the $text index and geo indexes, most of the time you'll be using a B-tree index, which is the default. And this is important so that your database isn't scanning all of its data every single time to every query to answer something. Okay, so this is, I won't go too far into the theory here, but this is what a B-tree looks like. And it actually arranges itself in, you probably guessed it, a tree with different leaf nodes that are aware of the range that they contain and the ranges below them. So this is how basically a lot of the indexes in Mongo work. It's not too important how, because the details are abstracted to you. But the goal is that the smallest amount of seeks happen possible in this tree to get the answer, and it's optimized in that way. How does the index work in Mongo. The optimizer actually, every time you're doing a find query, the optimizer, like most databases, asks what are the collections, or sorry, the indexes that have this field. So the list of fields that are in the find, we'll look through a list of indexes and try to find the best answer. So running a query without an index, and if the optimizer can't find one, you probably guessed it, it's going to just scan the entire collection to try and give you an answer anyways. And that's what we want to try and avoid. And we talked about it earlier that documents may be huge, but more importantly, the fields that you're indexing could be very huge. So we talked about data types earlier, that you kind of want to use the correct data types, but also consider that if you have very large data types, like a binary blob or a string that just has to be really long, maybe 1024 kilobyte of text, it would be nice to use an index that isn't that field and maybe something smaller, like a 32-bit unique ID. So the good practices for queries are maybe first create your app, unless you're very aware of what your indexes need to be. First create your app and start to look at some tools we'll talk about later to look at the performance of it, and actually try to see if your collection scanning. Percona's written some tools that should make that fairly obvious to you. But that's really leading towards the first point here, that don't create a lot of indexes. So some things I see in development a lot is just users creating tons of indexes that might not actually need to be there. And that slows down the optimizer and inserts and updates because they have to consider those indexes. Avoid duplicate indexes. I'll talk about that in another slide, that if you're Mongo won't necessarily tell you that you're duplicating indexes in some cases that I'll talk about on another slide. So it's probably better to just use tools to inform you that an index needs to be created versus guessing what needs to be created in advance. And the last point on this slide is important, that Mongo has directions for the indexes. So if you're sorting ascending in your application all the time, or let's say descending all the time, make sure your index matches that direction so that Mongo can be a bit more efficient in your sorts. And I don't have an example of that here, but in the find query, you can pass a sort and $sort and -1 or 1, which tells Mongo to use ascending or descending. Same with indexes. When you're doing a create index, 1 or -1 will tell it ascending or descending to match that up, if you can. And I just went the wrong way. Okay. So compound indexes, like most databases, you can have an index with many fields concatenated together, and Mongo will read them left to right. And that's important because they can be partially read. So in the green example, bold in the center here, we have username and 3 other fields. If I did a query on only username, Mongo can still use this index because it knows it can just chop off the rest of the index and just use the first, I don't know how many bytes the username is, but let's call it 16 bytes. It'll chop off the rest of the index entry and just use that first left half. Same if I wanted username and status, and so on. What that also means is you can create duplicate or unnecessary indexes. So all of the indexes in red under the green one are, aside from actually a spelling mistake between date and data, those are supposed to be the same on this slide. So actually, what I'm about to say is incorrect because of a spelling mistake, but let's pretend the second red line, the first red line says date instead of data. All of those would be duplicates because Mongo could just chop the first index left to right whenever it needed to get username, status, or date, also all 3 in combination, but spelling mistake, of course. So that's an important one. I'll just stress that a little further, that you could delete all of those indexes under the green ones, and that could be a massive win on disk space and maybe some cache space, because your indexes are pulled by the optimizer even if they're not needed. The optimizer does still have to consider them at query time, which means they might be in the cache and wasting some RAM. So at very least, getting rid of duplicate indexes will save you disk space, but it might also save you read and write performance and possibly RAM. So evaluating query performance, there's a lot of ways to do that in Mongo. We'll go through a few of those. You generally, in production, are trying to aim for low response time, so it's also important that the tools that you're using to analyze the problem aren't going to make the problem worse. But when you start off in development, you can definitely have a lot more metrics or granular details on what's going on in the database, because performance might not be as important, and later on you want to be a bit more careful about it. So it's nice to catch things like missing indexes and huge performance problems in development if you can. But also keep in mind that with small amounts of data in development, you might not see a problem that you will in production when you have hundreds of gigs of data. So just something to consider when you're evaluating performance. One of the best sources of performance data is the query optimizer in Mongo, which is similar to a slow query log in other databases, but Mongo writes to its own collection internally called system.profile, profiler data that will explain the performance of the query. But I'm actually on the wrong slide. I read optimizer and read that as operation profiler. On the flip side of the operation profiler is the optimizer, which is actually deciding the smartest way to attack the query that you're giving it. So I already mentioned that with a list of fields, it's going to look through the indexes and try and decide the smartest way to do this query. Hopefully you're using good data types and not too many indexes like we discussed to make that efficient. And on the other side of this, you'll have the operation profiler, which is going to tell you the after effects, what happened after the optimizer actually chose its plan and how long did it take. To evaluate index usage that the optimizer is using, you can use an explain on a find query. So basically taking a find query and adding .explain to the end will give you a full execution plan of what the optimizer is actually deciding to do. Just like MySQL again, select, I think with explain, I'm getting recipe in MySQL would give you something similar to this. And in bold on this slide, we have call scan, which is something to always look for in explain output to indicate to you that you're scanning data instead of using an index. If you saw IDX scan here, that would mean we're using an index to answer the query that we're looking at. If you see call scan, it's a collection scan, meaning there was no index to help the optimizer. So definitely a surefire way of telling that there was no index to answer the query. And I actually said IDX, it's IX scan in this example that's in bold, that's telling us instead here that there was actually an index on the namespace Percona foo, which would be the collection foo in the database Percona. So I already mentioned the operation profiler. That's going to come relevant now, which is showing us after the operation ran, what did the optimizer choose and how did it perform. So two ways to get the profiler data. One is through the log file and one is through what I just mentioned about 2 slides ago. Mongo actually writes that data to itself in a collection called system.profile. So we'll start with the log file. The log file, just like any app on Linux, there's a log file that writes out some data. Mongo will actually write out some performance data as well as errors, permission denied, disk is full, things like that. So every so often you'll actually see lines like you're seeing on this slide logged, and in bold we're logging some important parts that my eyes usually jump to, which are docs examined, number returned, and actually I would have put in bold also keys examined, which is just to the left of docs examined. And on the very, very end of the line in bold is the milliseconds that the operation took. So let's go through each of those things that I find important. Keys examined is how many index keys were scanned to answer the query. Docs examined is how many disk documents had to be scanned to answer the query. And returned is how many documents were returned by the query. And I already mentioned the last thing in bold on the first line is 691 milliseconds is the time that the operation took. So with the first command that I'm looking at on this slide, we can see that there was 897,000 documents scanned and 0 keys examined, the field just to the left of it. So that means to me that there was no index for this query. And there's another surefire way that I hope you've already seen, which is call scan, is also written to the log just to the left of keys examined. So both of those tell me there was no index. But what's worse is this query returned 0 documents and returned. The n returned field means how many documents were returned. So this query is particularly sad because it took 700 milliseconds and 897,000 documents to do nothing. It returned nothing, so it didn't find what it was looking for. If it had an index, that would have been a large index scan and no document scanned, which would be quite quick. So there's a lot of other fields here in the log file that I won't explain right now, but those are some great ones to start with as you develop. And your goal here, here's your goal example is ixscan, which isn't in bold, but key examined 1 and docs examined 1 is a good query. That means we read 1 index entry and we read 1 document. So that's an efficient query. And you can see it probably took no time at all, 2 milliseconds on the very end of the line. That's pretty quick because it used an index. So just looking at those 2 different things, the key is definitely keys examined and docs examined and the ratio between those 2. So I've mentioned the profiler, maybe a nicer way than just looking at the log file lines that you just saw. And to be honest, it's kind of hard to crunch data with your eyes from looking at that is the operation profiler that I mentioned. And it's a collection in Mongo, so you can query it with find queries. It's enabled with the set profiling level command or the operation profiling section of the configuration file. If you're in development, I would, or really, I enable this everywhere, including production, just at a sensible threshold. So usually 100 milliseconds is what I'll set it to. Anything over that will get logged, anything under that won't. In Percona's server for MongoDB, we actually have a random sampling of fast queries as well, because we also want to just have a random sample of queries that weren't slow. That's useful in performance and some tooling that we've created. Default MongoDB Enterprise and MongoDB Community, you can just set a threshold for slow queries, which is either log everything 2, which is the second line in the example, DB set profiling level 2, or mode 1 with a integer telling it how many milliseconds. So if I wanted 100 milliseconds, I would do set profiling 1, 100. That will enable the profiler I already mentioned will be logged to dbsystem.profile. That's a collection that the profiler writes to. And actually the same data that we looked at in the log files there, but it's nicer that you can sort it and pretty print it and do find queries on it for different things instead of grepping and awking a log file. And I actually forgot to add the last slide, but the operation profiler is actually used by Percona's monitoring and management to show you performance of MongoDB's profiler and queries that are happening inside of it. So we have a component of Percona monitoring and management called query analytics that reads, that we have agents that read the system.profile collection and send data to a central web interface and database that can actually show you the slowest queries in MongoDB, also MySQL, and I believe Postgres. While it's nice that you can do this query on the system profile collection and find, query, and sort it, it's even nicer if you have a web page that kind of does a bit more of the crunching for you. And it's too bad I forgot an example, unless it's further on in our slides. There's a lot of other tools out there that you can use on the command line. grep on the log file I mentioned is one. mtools is a Python project that is Mongo aware with the log file, so you can chop up the log file. And also, I'm doing this in backwards order. Percona has a query digest tool that is able to fingerprint queries, and using the system or the operation profiler again, fingerprint queries and show you which are your slow queries in the profiler data. And when I say fingerprint, I mean that we try and normalize queries. So if there's a query that says where user is X, we just make X normalized so that we know that that could be, X could be anything, and we'll just bulk all the queries with that field together. So it'll create a nice report, but probably not as nice as the Percona monitoring and management component I was talking about, which has a web interface. PT Query Digest is a command line tool that will just read the profiler locally, and it won't have historical data. The profiler is only 100 megabytes of capped collection, so the Percona monitoring system will actually have more historical data. This is an example of what the command line tool would output. So it's kind of the best we can do with the command line, a table that's breaking down the different aspects of this query. So this is just one query that the profiler found that's scanning 148 documents and returning 148 documents in this example. But as I said, it's nicer to see this in a graphical way. And the Query Analytics plugin basically will do just that. So I actually did remember to put one example here of, we're basically using open source technology. So I think this is actually using Grafana as a front end to actually show us that data. And we're able to, if we were to click on any of these singular options, we could break down further what they're doing. So get more oplug rs tells me that that's replication actually, but maybe that is a find on your application products, and you know that that's a query that's really important to you. If you saw a change in that performance throughout these dashboards, you could look at the explain output and also the change in efficiency. So if it went from returning 1-to-1 ratio of index to documents and all of a sudden it didn't, it would be a place to look where it's a little easier to look at than command line output. And I mentioned mtools earlier, but that's a Python tool that will do similar work to our PT Query Digest tool, but without summary. So it's more for chopping up log files based on, I only want to see collections with this name or this operation, things like that. And this is another log parser that's out there, the MongoDB log parser. So common issues that we see when applications are using the features that we talked about with Mongo, aside from duplicated indexes wasting space and indexes wasting the profiler time, are the aggregation framework misused. So one is unwind queries that don't have an index. I'll take a step back and mention that the aggregation pipeline is probably an entirely different topic to talk about, almost a webinar to itself. But there's different operations that you can pass through a pipeline that runs on a collection. And it tries its best to use indexes. But if you're using $unwind, which actually takes arrays and breaks them up into many separate documents, that's a common one to look out for that doesn't use an index, or can be slow if it's not using an index, basically. Skip is another one. Skip is if you're doing a find query and you want to skip a number of documents to a certain point, usually for pagination. It can actually take a little longer than you might think because it actually has to move through the collection to get to the next point. $where doesn't use an index and actually causes a global lock in older versions of Mongo too. $where can be used in find queries, but will actually create a global lock temporarily unless that's changed. We talked about collection scans, but basically if you see a lot of those, they can bring your server down, not just in a way that you know, your user's inbox or something is taking a long time. It can actually bring servers down to the point that they can actually appear down. So you shouldn't get to this point too often, but if you write an app that suddenly becomes popular and wasn't maybe yesterday, and you weren't using indexes and you have enough collection scans, all of a sudden, you can actually, I've actually seen hosts that I can't SSH into because the load has gotten so high, things like that. So something to, again, worry about before there's lots of data is, are you collection scanning? And that's another common theme with all databases, Postgres and MySQL, that if you're going to scan all the data every time, it's going to hurt a lot. If you're querying the oplog is used for replication. It doesn't have an index either, so it always runs a collection scan. And that's something to think about if you're running backups with oplog or using the oplog in your application. I didn't mention it in this talk, but there is a feature called change streams in Mongo, which uses the .watch function on a find query to watch for changes. If you're using the oplog for your application to get a stream of changes, I would try to move to change streams, which Percona has some data out there on. Also, server-side queries is another one. So there's an operation called .currentOp in Mongo that will show you all of the server-side queries that are running, and some queries won't show up in that, like MapReduce that's using the JavaScript execution engine, which is another thing I didn't mention because it seems to be going away in replace of the aggregation framework, MapReduce. Which actually lets you pass a JavaScript function to Mongo to actually run on data. And that's not always going to show up the way you expect as an operation in current op. Another common issue is just spilling over to disk is what I usually call it when you have a set of data that completely fits in RAM, and on day 36 of your launch, your RAM is full, and now you're starting to read from disk. That can be a surprise to some if it hasn't been tested, disk performance versus RAM, and that can be a common problem. And just think about it and monitor that, your cache sizes, because once you run out of cache sizes, you're going to start hitting disk more frequently. And it can be a bit of a cliff sometimes, especially in high volume apps that had a lot of RAM, maybe hundreds of gigs of RAM, which hides lots of problems until you're out of that RAM and now we're reading data from disk. That can be usually a time when you notice that you're collection scanning, because collection scanning happens very quickly in RAM. You don't really know that you're doing it, and you have 128 gigs of RAM, which is becoming more common today, and it fills up to 127, and all of a sudden you're finding out the real performance of your disk in production because you were reading from RAM the whole time. So that's another common problem. But yeah, to wrap up, the keys are really, we started at the very beginning with the document, making sure the document is as efficient as possible. Secondly, your use of the operators, which was the second section, and basically using things that are smarter, like using $in instead of $or, and also just knowing how those things work is important. Third is adding the correct indexes, not too many, and getting that just right. And then really the fourth key is if you got any of that wrong, or you missed something, or there's a new performance problem, how do you find it? And really, we looked at some command line tools. I encourage everyone to go look at our demo of Percona monitoring and management, pmmdemo.percona.com, because I didn't have quite enough slides to really express the usefulness of the query analytics plugin that's using the operation profiler. So with those kind of 4 sections kept in mind, you should be able to avoid the major common performance problems, and you can always reach out to Percona or look at our other material if that doesn't work out for you. Any questions?
Thank you. Yes, there are a few questions. Our first question is, what's the alternative option to skip, and then there's parentheses at the end of that?
It should be limit, if I'm understanding the question. So there's .skip in parentheses, and .limit would be the limit of how many documents after the skip you wanted. And .limit can be used in any query without skip also. So with no skip, limit just limits from 0 to your limit. So 0 to 100 if you said limit 100.
Thank you. Our next question is, how do you decide the working set plus indexes fits in the RAM? Like, what is the working set?
Good question. So the real answer is it's not always easy. The best way to predict it is using math. If you know, I'll take a step back. So because Mongo can have schemaless documents, so documents can be, one document in a collection can be different from the other. Let's pretend that's not happening. So every document has the same fields. Just to make this math a bit easier, you can take a document in Mongo and actually look at its bson size using the bson.bson size function. And from there, you can extrapolate if one user takes 28 kilobytes of data, in my database, 1 million will take up this much. And you can start to do math on how much RAM is needed. That doesn't sound, as I'm explaining this doesn't sound very fun, but yeah, you can actually do that with math. The other way is a load test and try and simulate a lot of data being written at once. There's some tools for Mongo that do this, like Mongo Replay and Flashback by Parse, which are able to record Mongo traffic and replay it. So one thing you could do is replay your production now and maybe, record your production traffic now and replay it at 10 times the speed to try and see when it would spill over. But yeah, it's not an easy answer. Of course, the one part I didn't explain there is you need to know how much memory you have to be using to be caching data. But yeah, with those numbers, you can at least guess. And Percona is also working on a lot of kind of prediction, for the lack of a better term, in PMM, so that at least in the future, if we know that disk space is always growing by 10%, we can kind of draw a line in our graphs that will allow you to kind of predict if it keeps growing at 10%, when is it going to fill. So hopefully Percona can make that easier in the future, but for now, try and do some math or load test.
Thank you. Let's see, our next question is aggregation query take indexes? Does it like run through a working set plus memory or from disk?
It will use Mindex if you do. So an aggregation pipeline can have many stages. If you use a $ match in the first stage, which is just like a find query. In fact, you can copy and paste a find query into a $ match stage. That will use an index. But really the intention of the aggregation framework is to use an entire collection as the input to the pipeline. So it wasn't really designed to use indexes, but here's the good thing, that if you use $match as the first stage in your aggregation, it will. So that could be a huge benefit if you only wanted to look at, today, aggregate only documents that have timestamp less than 24 hours, and you had a year of data. The aggregation will only scan to what you asked in the match if it's the first stage. And I think there was a second part of that question, or do you think that was it, Emily?
I think the other portion of the question was, is it better to work in memory, or does it work from disk?
Right. The aggregation pipeline will use 100 megs of memory at maximum for its own, I guess, buffering and sorting. And it can actually exhaust itself if you do a big enough aggregation, and it'll actually return an error in this case. If you get that, there's a flag, I believe it's use disk true, but it'll be, if it's not use disk true, it'll be almost the same name, different words, that actually allows the aggregation to spill onto disk. So I guess to shorten that, it'll use 100 megs of memory by default unless you tell it can use disk, which is optional. And it'll perform much better using memory, of course, and a $ match if you can.
Great, thank you. Let's see. Our next question is, how do we find the latest query? Is it in the working set or not?
The latest query. I think, I'm not sure if I completely understand the question, but the latest query, let's see how I can answer that. You can definitely, in the operation profiler, if that's what you mean, you can sort the operation profiler by time and limit 1. So if you did that, if you did a backward sort limit 1, you would see the last flow query in the profiler, if that's what the user's asking. But I don't really know how that would apply to the working set. So I feel like I don't quite understand the question, but hopefully that helps.
Let's see. Our next question is, how can we force clearing the RAM if it's exhausted?
So if the RAM is exhausted, so if you hit that error in an aggregation, the RAM is cleared because you hit the error, basically. So if your aggregation uses the 100 megs and hits the error that says, hey, you used too much memory, that memory by that point had already been cleared by the server. So really the server is managing that for you. If you wanted to clear, let's say, the file system cache, or what is in the WiredTiger cache, which I don't think the question is, but just in case, you can restart a MongoDB is one way. that I can think of, which would basically start your cache from empty. Yeah, those are the ideas that come to mind.
Thank you. Our next question is, in aggregation pipeline, and there's a dollar out, by default creates a new collection. Is there any way to append to existing collection?
I think there is. Actually, by default, it doesn't create a new collection, but that is an option to the aggregation you can pass, which is out, which will write it to a new collection. I don't use that too often. I think the answer is no. I think the collection can't exist in advance, which would be really to your question. No, I don't think it'll support that. There's probably a different way around needing to do that. One way is you can use an aggregation as the input to a for loop. And using the for loop, you can do inserts to a different collection. But just using the out feature of aggregation, I don't think it'll let you. I think the collection can't exist in advance.
Oh, thank you so much for that, Tim. Well, looks like we're actually have addressed all of our questions today. So I'll give everybody back, a couple more minutes back in their day. Thank you so much for joining us today as we talked about how to improve MongoDB performance with proper queries. And huge thanks. Thank you so much, Tim, for presenting today. We learned a lot.
No problem. Thanks, everyone, for joining.